Hi guys, welcome to the video tutorial for chapter 5.4. Today we're going to be looking at magnetic objects and fields. So let's get right into this. So as you can see, we've got a lot of learning objectives, but the concepts are pretty simple to understand and a lot of similarities to what we've learned previously in the electrostatics unit. So our first learning objective is to draw magnetic lines around a bar magnet, marking in their direction with arrows. So below you can see a diagram of a north pole marked by the N and a south pole marked by the S. And you can see that the field lines are somewhat similar to the electrostatic charges. Now what is somewhat different in between here is that the north is meant to point to the south pole, and so the diagram is pretty straightforward. Okay, so you can mark some additional arrows on here, which I'm doing in orange right now, and for some lines that point 180 degrees away like this one, it just points straight out towards infinity. And here we have a line coming in from infinity towards our south pole. Okay. Normally I would recommend drawing about 3 lines is usually pretty good to get the marks for your, to demonstrate your knowledge for this, okay? All right. So in the same sense, I like to use, I purposely use the red color for the north. And you see that this is a pretty common convention as well, because just like the positive charge, those arrows points away from the north, and the blue, sorry, well, I have a negative for my blue. That's, just noticed that right now. So the negative charge is the south, and then so it's meant to point towards the south pole, just like a negative charge does. Okay, on to our next 2 learning objectives. Distinguish between the north pole or the end pole of a magnet and the north pole of the Earth. Third learning objective, know that there's a south pole at the north pole and describe the shape and direction of the Earth's magnetic field. So Earth's magnetic field, the shape of it is, I guess you could sort of describe it more of a bit of an oval shape in some ways. Or you could describe it as sort of like a figure 8 in some ways. So they do, it is circular around the Earth, but in terms of from the Earth, you can see this sort of almost like a butterfly shape in some ways is another way to describe the shape of the magnetic field itself. Now, I want to just clarify here 2 different terms, because we talk about the south pole being at the north pole being at the south pole, and things like that. So I like to use, I would recommend you guys, this is sort of like an exam or question answering. It's also just to clarify things, exam tip here. So 2 words here, magnetic can be combined with north or south. And then we have what we call a geographic, north or south. So when we normally talk about north pole in an everyday language, we're talking about a geographic north, and our compass points, well, we think of it, I mean, everyday people think of it as pointing towards the geographic north, but it doesn't actually point the geographic north. It points to a magnetic south. So that's what we were talking about up here. If you can see that quite clear in this diagram is, I'm going to use the pink here to mark that. So over here, the tilt of the Earth, this is the geographic north. Geographic N, and this is the magnetic south or south pole. Okay, so it's really important to use those extra terms before you describe the north or south, magnetic or geographic. Otherwise, people will get very confused about that. So this is directly related to the same diagram. This is the same as the diagram we had up here, right? Everything points to the south. So that's why the learning objectives here looks kind of contradictory in what we're seeing right now, okay? And of course, you can see that because of the tilt, the magnet isn't perfectly aligned with your geographic north and south. So this is one of the main reasons that the magnet itself will be tilted, will have a tilt. So you can kind of imagine, this is actually kind of obvious, like right here. If you were standing at this particular point, whoops, I'm trying to draw on that. Okay, it's not letting me draw. Okay, there we go. So if you're standing at this particular point, notice that the magnet would actually, it does point towards the magnetic south, but it's also tilted as well. So that's why on Earth that you will discover that the compass magnets, the compass itself will be tilted in a bit of an alignment. So our next learning objective is to draw magnetic field lines in between two bar magnets. Now we've kind of seen this example when we're looking at charges, right? So you can almost think of this as two positive charges. And this is exactly the same diagram, okay? You can replace it directly in many ways. And if you were to ignore that there was any sort of a south pole, this would in theory point outwards as well. But we usually leave that because there's usually a south pole, and that's why they don't have the arrow pointing out there. Now, this is a monstrosity of a diagram, which we never talked about. This would be the equivalent of having 4 electric charges. This is what that diagram would kind of look like, okay? So actually, if we had something like a positive charge here, I'm just going to do the positive charge over here, right? And then we had 2 negative charges. This is actually what that diagram would have looked like, but it was never required for you to see 4 different electrostatic charges together. But this is actually the diagram that you would actually see. And actually, in between this, I'm going to use a bright green. You would actually see a line like this form. Okay, so it points away from the positive towards the negative. But when we do magnets, we don't usually include that line. But if we were doing electrostatics, you would actually see that line in between. So you would see this, and you would see that as well. Okay, but that's for electrostatics. And that's where there's some similarities, but also differences between our magnets as well. Now, one of the other things that we're going to connect here is the density of the lines. It has to do with the strength. So the greater the density, the greater the strength, which means if you were at a point here, let's say, I'm going to call this point A, this would have a high, I'm going to use a slight dark color, this would have a high field strength or density. Whereas if you were something maybe like over here, let's call this point B, this would be a low field strength. Okay, and likewise, I think we got some other diagrams here. So here again we have, trying to zoom in. So here another, again, we have, this would be very high density. Very high density. And as a result of that, the magnetic field strength here at this particular point, I'm going to call this X, would be very strong, okay? At less dense points, maybe like here, let's call this Y, this would be low strength. Okay, because I'm zoomed in, the words looks like they're really thick. Okay, so that's another 2 learning objectives done. Our last learning objective is to understand the compass needle is just a very small magnet that's allowed to swivel or flow or move freely. And here we got a rough little diagram. And again, perfectly, I just talked about the tilt of the magnet of the compass, okay, which was due to the magnet not being perfectly aligned geographically. So if you were flat here on Earth, okay, the magnetic field lines are sort of at a bit of an angle like that, okay, and that's why it tilts, okay. So the compass itself is a small magnet. It's a small, what we normally call, usually they're ferromagnets, or they can be made into magnets by being in a magnetic field for long periods of time. And then so it'll align itself along the north-south pole axis. So let me just maybe talk a little bit about how the compass works. So if we had the compass here, what we would do is we would draw a tangent to that, and it would point along that tangent. So another example is maybe like right here. So again, we draw a tangent to the point, and it would point towards that, okay? So here again, I guess we can take another point right. Oops. Right here, okay? And so again, we draw a tangent, and it points along that tangent. So at any point, draw a tangent, it's going to point in that particular direction, okay? And that's how magnets are meant to work. Okay, below I've got two activities here. So in this diagram, I want you to draw the magnetic field lines, or the compass lines, okay? I guess the direction the compass points in. Compass direction. Okay, at points A, B, C, and D, okay? So take a moment, pause the video, and go ahead and do that. Okay, so hopefully you've paused the video and you've had a quick chance to think about this. Let's quickly go over the answer. So we just want to draw some tangents here, and this is pretty straightforward. Now D and C are kind of tricky. Now C, if it was perfectly in the center, it would actually not experience a field. Or you could say it experiences an equal field from all directions. Okay, or that all fields are equal. So in essence, they all cancel each other out, okay? And, sorry, the timer going off. D, depending if you have a south pole or not, could have an arrow, it could not have an arrow, but if you assume that there isn't one, normally we don't normally test that, okay? So you could draw an arrow going out, but normally we don't have anything like that. So these are a little bit of a trick question. Depends if there's a south pole there or not, okay? So south is meant to point towards north. So if there was a south pole, it would actually point towards the north in some ways, okay? All right, next activity is at which point is the magnetic field the greatest? We've kind of talked about this already, so take a moment, go ahead and see if you can respond to this. Okay, so hopefully you've had a chance to respond to this already, and so essentially it's going to be points C is going to be the greatest field density, so the answer for this is going to be C. And D, in case you missed it, is over here, would be the weakest density, okay? All right, guys, that's it for today. So pretty easy lesson so far. We'll see you guys next time. Take care. Bye-bye.